In this video, we're going to cover section 9.7 on the hydration of alkynes. Now, similar to alkenes, alkynes also undergo hydration reactions. And so the first reaction that we'll look at is referred to as acid catalyzed hydration. And the reaction conditions are slightly different than what we observe for alkenes. You'll notice in this example that the catalyst that's used primarily in this reaction under acidic conditions is mercuric sulfate, HgSO4. And so HgSO4, in the presence of acidic media, in this case sulfuric acid and water, we will observe the hydration of an alkyne. Now, we will show some of the mechanistic details on the following slide, but we won't show how mercuric sulfate is actually incorporated into the mechanism. So again, not so much a testable mechanism, but it is important to understand the details so that you can follow the regioselectivity of this reaction. And we'll explain more about that in just a moment. So you can see when we hydrate an alkyne, one of the pi bonds of the alkyne is going to interact with those reagents. And the net product from this conversion is what we refer to as an enol. And so similar to alkenes, we're going to have the hydroxyl group forming a new bond to carbon of the original alkyne that's more highly substituted, and the hydrogen will end up on the carbon of the less highly substituted carbon of that original alkyne. And so specifically here, we're looking at a terminal alkyne. Okay, so there's a hydrogen attached to this particular carbon. And you will see that the hydroxyl group will end up at the carbon that's more highly substituted. Now, we don't observe this particular product in our mixture. What we often observe is the ketone. And so the enol, although it's formed during the reaction, it's difficult to isolate. And so what will happen in that same reaction mixture is this enol will undergo a rearrangement, referred to as a tautomerization. And that results in the formation of a ketone. So this is one of the first reactions that we've looked at in which we're now producing compounds that contain this carbonyl group, the ketone, in this example. So you can see that this carbon is this carbon in our enol. And so to either side of that carbon, we have an R group, a carbon-based system. And so in this case, we have our R group. And because we're working with a terminal alkyne, the other alkyl group of the ketone will always be a methyl group. So the initial product, as we said, is the enol, which comes from the fact that we have a double bond still. Only one of the pi bonds is reacting, so we still have one remaining pi bond to give you that alkenyl structure, and we have the hydroxyl group. So enol, this is where this name comes from. Now, if we were to start with a internal alkyne, meaning we have two R groups on either side, if those R groups are not the same, then we would produce a product distribution of two different ketones. So because of that, the synthetic utility of this reaction is generally preferred to start with terminal alkynes so that we only end up with one ketone as our final product. So now let's look at how this enol undergoes a transformation to the ketone, a process which we refer to as tautomerization. So in the acid catalyzed conversion of an enol to a ketone, it occurs via two steps. We first have a proton transfer that occurs between the enol and H3O+, that's our acid. And so you can see the pi bond of the enol is going to accept a proton. It's acting as a weak base to pick up that proton. forming this carbocation intermediate. This carbocation intermediate, because there's a neighboring atom with lone pairs, we can draw a resonance structure for it, which in this case will form the carbonyl, a oxonium as well. And it's then the proton attached to that oxygen center that's picked up by water in our reaction mixture. So again, we refer to this as acid catalyzed because there's an acid used to promote the formation of our intermediate, and then we regenerate the acid in the end. So in the presence of the acid, we have proton transfer, and then water present in solution is used to neutralize our resonance stabilized intermediate to give us our final ketone. Now the enol and ketone are said to be tautomers of one another. They're constitutional isomers, but they are not resonance structures of each other. There needs to be that interconversion between them where we really have a migration of a proton from the hydroxyl group to one of the carbons of the ketone. But it's assisted, it only can occur in the presence of that acid. So this interconversion is referred to as the ketoenol tautomerization. So this is one method of hydrating an alkyne to give us a ketone. Now let's look at a second method. So in this method, we're using hydroboration oxidation conditions. And as you'll see, we'll use, similar to the alkenes, a boron-containing compound, so borane in this example, followed by an oxidation step, which involves peroxide, hydrogen peroxide, and sodium hydroxide. You'll note in the following slides that the choice of the boron reagent will differ than what we observe with alkenes. This reaction will go with BH3, but it's not the preferred boron-containing compound. So we'll look at other boranes that are used for this reaction. Nonetheless, as you can see, this reaction involves the anti-Markovnikov addition of that hydroxyl group. So yes, we do have this intermediate enol also prepared or formed in this reaction, but note that the OH group, the hydroxyl group, ends up at the least highly substituted carbon of the original terminal alkyne. So in this particular reaction, the observed product after the interconversion is the aldehyde. So instead of forming a ketone as we observed previously, aldehyde is our major product. So again, we can't isolate this enol very easily. It's very difficult to isolate. There will be this base catalyzed tautomerization that occurs in a very quick manner. So let's look at the details of that tautomerization relative to what we observe for the acid catalyzed version. So please note that under hydroboration oxidation conditions, we're working under basic conditions. These are base catalyzed reaction conditions. And this is very different than the acid catalyzed hydration of an alkyne. So the order of the steps involved in the enol to aldehyde conversion, the tautomerization, is different. When we're working under basic conditions, we're never going to observe positively charged species during our mechanism. Similarly, under acidic conditions, we're never going to observe negative formal charges. And so in the first step of this tautomerization, it's not the enol accepting a proton. There are no protons available under these reaction conditions. In this particular situation, the hydroxide ion is accepting a proton from the hydroxyl group of that enol. And so the first proton transfer step is the hydroxide accepting a proton from the enol to generate an anion as your reactive intermediate. This anion is referred to as the enolate ion. And you can see, like we saw in the previous mechanism, that this is also resonance stabilized. And so we can draw a resonance structure that represents the enolate ion. What we observe is the formation of this carbanion, and it's this carbanion that then picks up a proton from water present in our reaction mixture, and that generates the neutral aldehyde. So under basic conditions, we're going to see deprotonation of the enol first. That will generate a resonance stabilized intermediate that we refer to as the enolate ion. And then that enolate ion is protonated to give you your final neutral aldehyde. So in this section, we've seen two hydration reactions for alkynes. And they're regioselective in the sense that we can determine where we want the placement of that carbonyl in our original alkyne. So if we wish to form a ketone, which in effect is placing a carbonyl at this position of our carbon backbone, we would use mercuric sulfate under acidic conditions. So typically it's a mixture of sulfuric acid, water, and then mercuric sulfate. Under those conditions, we will regioselectively form the enol that places the hydroxyl group at this position, and the tautomerization will result in the formation of a ketone. Now, under hydroboration oxidation conditions, the opposite occurs, that we have anti-Markovnikov addition, if you will, in which the original hydroxyl group of the enol will end up at this location, and then following base catalyzed tautomerization, we end up with the aldehyde. So from a terminal alkyne, this is what we will observe. Now please note, in the hydroboration step of the hydration reaction, that typically a dialkyl borane will be used as opposed to borane, which was shown on a previous slide. So you'll often see this designation to represent a dialkyl borane. And the two most common dialkyl boranes are very sterically encumbered boranes, and that's to reduce the reactivity of the borane reagent to the second pi bond in the alkyne. Now, we won't go into the details of how they're used, but I want you to be aware that on Wiley+, occasionally in place of R2BH, you'll see two other reagents that are used. And they are the dicyamyl borane and the 9-borobicyclo nonane. So you may see these two terms used in place of the R2BH. So I want to make you aware of that when you're working on the assignment. So if you have any questions about the hydration of alkynes, by all means send me an email, and if required, we'll meet via Zoom to discuss it in further detail. Thank you.